Chinese nuclear scientists have created an artificial sun that's reached a temperature of 100 million degrees Celsius. That's 6 times hotter than the core of the natural sun. Experts say the step is an important milestone in the global quest to harness energy from nuclear fusion. Dr. Matthew Hole is an Associate Professor and Research Fellow in the Mathematical Sciences Institute at the Australian National University, and he joins me now from Canberra. Dr. Hole, welcome to Mornings.
Thank you very much.
Could you please try and explain in layman terms what this artificial sun is and how fusion energy works?
Certainly. So fusion is the process, it's the opposite process to fission. So fission, you fragment heavy nuclides to produce something which is lighter. Fusion is the combination of light isotopes, typically of hydrogen, to form helium, which is an inert gas. So in the sun, what happens is the proton-proton cycle, hydrogens collide together to form helium. What we're trying to do on Earth is to reproduce that. So these hydrogens collide together to form helium. In the process of doing it, they produce a very large amount of power. They also produce a neutron. What we're trying to do is harness that reaction in what's called a tokamak, a toroidal confinement facility, and produce ultimately net power out of the device. So the intrinsic advantages of fusion is that it produces base load power. It's intrinsically safe. It can't melt down. The fusion fuels are ubiquitous. They're found all over the world. And the experiment itself and the reaction can't be used for weapon proliferation purposes. So it really is a long-term ideal solution, particularly in the light of environmental and climate change concerns.
So how significant is it that these Chinese scientists have been able to reproduce this in their artificial sun?
So it's a significant step for the Chinese fusion program. The Chinese fusion program has made leaps and bounds over the last 20 years. They have 2 major experiments. The experiment which is in Hefei, which is the East experiment, which they're quoting. There's another experiment in Chengdu, the HL2A experiment. This is a significant step both for their program and also through that the international fusion research program, because China contributes to the ITER program significantly, and much of their domestic research activity is leveraged or built upon these experiments. So it's a significant step for the Chinese program, and it's also through that and through the international contribution and effort of the Chinese, a significant step for the international program.
Well, you mentioned that this is all about harnessing power, and as we know, we've had somewhat of an energy crisis here in Australia. Could this provide a silver bullet to our situation here with regards to energy?
I think in the long term it could. Fusion is a technology that will still take 30 to 40 years probably before it is commercialised. And the reason for that is simply because you're trying to achieve something that is incredibly difficult to do. You're trying to recreate a star on Earth. So this is much harder in many respects than putting man on the moon. And so fusion has made stellar progress since the 1960s. And ITER, this next step experiment, will basically prove the scientific principle of fusion power, but that experiment won't be completed until effectively the end of the 2020s. So the first fusion plasmas are around about 2025, paving the way for full burning experiments in 2030. So there are fusion power plants projected around about the late 2040s. So could it be done faster? Sure, if there was political will to do it. I'm looking at the scale of investment internationally required to produce fusion power at present. So that in turn the question is, could it be a component of Australia's energy future? Sure, but it's not going to happen within the next decade.
Because there's no political will here?
That's not quite the reason. I mean, there's a twofold reason, one of which is that the field of research is now completely global. So in the same way that high energy particle physicists go to CERN in Switzerland to collaborate, fusion scientists from Australia will go to ITER and other international experiments to collaborate. So the 2 parts of this is that the rate of development of fusion energy is an international time constant. It's not set by Australian time constants. But the second part of it is that Australia really needs to have a fusion science activity, otherwise it won't be able to leverage these opportunities or indeed be able to deploy fusion science or fusion power when it becomes available. I have no doubt it will become available. It's going to be a matter of timescale.
So what needs to happen here in order to start developing that so we can have some sort of nuclear fusion plant here?
Well, Australia has had a long association with fusion science. Indeed, the fusion experiment or the fusion process was co-discovered by Sir Mark Oliphant way back in the 1920s, or 1930s, sorry. Today, Australia has world-class expertise in plasma imaging and diagnostics, plasma theory and modelling, which is my own field of research, and material science. And we have international access to the ITER project and the surrounding research activity. What we do need is we need dedicated government support, either in the form of fellowships or human capacity, ideally permanent positions in the field. What we need is we need an Australian flagship contribution to the ITER project, which will be a coherence imaging diagnostic for the diverter region, and we need associated infrastructure support that enables us to deal and produce an activity in material science that's relevant for fusion in the long term.
Dr. Hole, you mentioned that this process of nuclear fusion is entirely safe. Is it guaranteed 100% safe?
It's, the difficulty with fusion is not letting it run away, it's initiating it. It's a very difficult thing to initiate and sustain. So it is 100% safe to background, even in the worst case possible scenario for a fusion power plant, which I've been involved with in terms of studies, and or for the ITER site itself. The maximal damage is primarily to the machine itself. There is no level of background, there is no danger to the safety of the general public at the site perimeter. So there is no risk to the general public at all. It is completely unlike conventional fission technology. There is a risk to the experiment itself in terms of you're damaging an expensive piece of equipment, but that's an infrastructure risk, not a public safety risk.
And how much is a machine like that?
So the Next Step project, ITER, has a price tag of around about 30 billion Australian dollars. That price tag maybe end up being more than that. I mean, it's a question of, this is a first of a kind of experiment. So it sounds like a lot of money. It's a drop in the ocean by comparison to global energy expenditure. It's totally insignificant by comparison to the cost of the Joint Strike Fighter. It's all relative. So fusion, yes, as a single experiment, the ITER project is expensive, but is it worth it to find a baseload energy solution that might be able to provide a power solution for sustainable society? You bet it is.
And has this idea been at all in discussions at government levels when discussing Australia's baseload power issues?
It's certainly been in discussion in a research and science investment context. I think because Australian energy markets tend to be on the lookout for of the order of 5 to 10 years, I don't think it's been on the radar in terms of very long planning. There has been various studies, one of which is by the CSIRO, which includes nuclear power as some level in Australia. I think primarily those reports are focusing on conventional fission technology. I don't believe, to my understanding, there has been a component of fusion power in that energy mix in the long term, but of course I would welcome that very much in a policy debate.
And just finally, Dr. Hole, you mentioned that there is no chance of any of this energy being harnessed for evil, if you like. You cannot weaponise it.
No, that's right. You can't weaponise it. I mean, part of the reason why is because, as I said, it's very difficult to initiate. The fusion fuels are deuterium and tritium. Tritium you manufacture by activating lithium. But in order to initiate a weapon device, you would need a thermonuclear trigger, and that trigger is almost certainly, well, it is a conventional nuclear weapon. So you need to include fissile ingredients to weaponize it. And if you look at a tokamak fusion configuration, it is totally inappropriate for that configuration to be weaponized. It's just the wrong set of tools.
Okay. Well, lots to think about there, including bringing back memories of the periodic table. Dr. Matthew Hole, Associate Professor and Research Fellow in the Mathematical Sciences Institute at the ANU. Thank you.
Thank you very much. Thank you for your time.